back in operation. Reconnection successful, so okay, that's good. So I guess that it's better than me not to follow this streaming. It says that the connection is very good. That seems not to be a problem. And let's see. Yeah, you guys are able to see me, but when I'm looking the number of viewers, that number seems to be 0. Don't know why. Okay. Maybe because I just put the system on, so it still needs you a little while to see. Okay, so there is that the live streaming is not on. Should be on. Okay. Okay. How is it now? Let me check my mails. It says that I'm live in the YouTube. Okay, so yeah, you guys are here as well. I see your comments. Sure. Yeah, I'm sure, yeah, it makes sense to start it a bit earlier, because for some reason the streaming key is always changing. I actually don't do any other streaming than this lecture, but for some reason it seems that I'm not clever enough to set the streaming key to my OBS. Anyways, up and running, so this is a link. And again, I'm apologizing that I'm late, but that's not gonna happen next week. This time I'm 10 minutes late. Next week I'm gonna be 5 minutes early than the usual time. So I got the some information that it seems that it kind of like uploading some material, but okay, it seems to be okay. So I see that we have 53 viewers this time, and it makes a little bit of complaints that the data stream is not as smooth as it's supposed to be. Okay, so maybe because maybe because I'm using my mobile phone to do the streaming, so this is my internet connection, so maybe that's the reason that is not cooperating in a way that that is supposed to operate. So I can see that complaints are coming, so you guys are not pleased about the connection quality. Okay, let me see if there's something I can do in that regard. Maybe that the best thing to do is that I will close all other windows. And that should help. Okay, so somebody's giving me an advice that I should try to reduce the quality from 720 to 480. But it seems that it's getting better now. So it seems that it's getting better. So finally we are okay. Yeah, so it is actually a phone. It's not a potato. It's not a potato. But anyway, so I think it looks to me that we are finally good to go. So lection number 2. What's going to happen in lection number 2 is that we will kind of look back what we discussed last week, and we need to still continue to discuss some matters. And there's some important thing which we still need to discuss is this description of rigid bodies. Why this is important? It's important because it's an essence of dynamics. An essence of dynamics because it describes what are the rules that the system is described. So what follows after that is that we kind of mechanically use these rules, which is this equation that we learned last week, and the equation I'm going to write it here. So it's going to be based on this equation, which says firstly that we first look at the translation of the body reference coordinate system, and then we're gonna rotate the system and account the rotation by using this transformation, this rotation matrix A, and then using the body reference coordinate system and with the Gbar we can scan every single particle in the body. So that's the equation that we're going to use mechanically over and over again. And now what follows when we're going to proceed in the course is that this description of position will be differentiated with respect, and I suppose no surprise to you is that we're going to get the description of velocity. And once we differentiate the description of velocity, one more time with respect to time, we will get the description of acceleration. That in turn is very important because we eventually wanted to use a Newton's second law, which says force is equal than the mass multiplied by acceleration. So it essentially says external applied forces is equal than inertia forces. Now, as you see, the inertia forces is a mass multiplied. That's where we need this acceleration. So once that is done, then we're going to look at the concept that is called tenorized coordinates. Extremely important component and concept, because everything from that on will be described based on tenorized coordinates. So we will no longer use a global coordinates or anything like that, but we're going to use tenorized coordinates to describe forces, constraints, so on and so forth. And then once that is done, then we're going to look at the constraint equations. So with that, it's I'm still gonna get the arrows every now and then. I don't know what's up with that. It seems that my connection should be okay. Maybe the one thing that I could do is that I can put my phone closer to the window, and as you can see, my office here is located in the basement. So this is maybe the reason that the connection is not that strong as that it could be. Okay, so hold on. So like that. Still, I have this connection problem in my stream. Okay, so let's move on. So we here. Weekly homework. Few advices related to weekly homework. First of all, as I mentioned last week, please use a symbolic math tool, because that's going to be super handy to you when you're actually preparing yourself to midterm exam. And as mentioned earlier, you are allowed to use a symbolic math tool in midterm exam. So kind of familiarize yourself already this time to symbolic math tool, and you can use whatever tool you feel that is appropriate to you. So you can use a Maple, MathCAD, MATLAB symbolic tool, or whatever you want. Now, once you're ready with the first weekly homework, please use a PDF submission format, or if you decided to use a handwriting, you need to scan the handwriting or take a picture of that and convert that to be PDF. Some of you ask how you can do the submission. So here are the instructions for you. So the instructions go such that you need to select the period number 1, which is this period that we are experiencing right now, and then you need to select topic number 2. Now, first week submission mailbox is actually in a topic number 2. This week's submission mailbox accordingly is going to be located in a topic number 3, and so on and so forth. So with that, I figured you got the concept. And now a request that I got from LUT administration is that they hope that I can provide you a little bit extra time to do the homework. And the reason being that some of the students are getting started on 14th of September, and they should have some time to do the first weekly homework. So the deadline is not on Sunday as it used to be, but instead it's going to be 16th. That's, I think, that's a Wednesday. And the deadlines are always in midnight. And I mean, to be precise, they're always set to be 23:55. And that's firm. So if you try to submit after that deadline, the system is already locked and you're unable to do that. So keep that in your mind. So there is no flexibility whatsoever. Also this week, guided tutorials will be on. So 2 opportunities to get help from Suraj. And those opportunities are Wednesday from 8:15 to 10 o'clock. You can get the help online. So Suraj will not be in a lecture room 216, but instead he will be available online. So that means that if you have a own personal computer and if you were able to install the software, my recommendation is not to go these computer classes, but instead stay home or whatever place you feel that is quite uncomfortable and do these tutorials in that place. Please know that there is no mandatory participation to tutorials. So they help you to do the simulation assignment that will be provided to you a bit later, but is not requirement, is not mandatory to participate to tutorials. Okay, hope that is that's clear. So, summary from last week's lecture. So last week's lecture we spent quite a bit of time and we looked at the concept of multibody system dynamics, and we learned the basics of kinematics, which is needed to describe particles in multibody system. And we learned that the multibody system, by the definition, is a system that consists of multiple bodies, as the title implies. And the very, very important concept in these multiple bodies is that they are connected together via joints. So there are mathematical descriptions regarding the limitation, motion limitation of neighboring bodies. That is joints. So joints are really essential components in multibody system dynamics. And this concept we can apply to pretty much wide variety of applications. So we can apply that to robotics, mechanisms, heavy machineries, whatever you want. So pretty much everything is possible, including the biomechanics. Now, something that is extremely important regarding the multibody system dynamics, which I did not mention last week, is the fact that in multibody system dynamics, we do not make any assumption regarding the magnitude of rotation. And this is a conceptually very, very different that you are used to deal with. Because if you look at back your notes from the courses like Dynamics 1 and Dynamics 2, the most often used assumption in those courses is that you're assuming rotation to be small. Let's say that we have a pendulum like this pen. So the small rotation means that there is a pendulum that can move, say, plus minus 10 degrees, plus minus 15 degrees max. This is a limitation we don't have in multibody system dynamics, but instead a body can rotate as much as it wants. So we can easily deal with a pendulum where the initial configuration may be horizontal like this one, and then the pendulum is moving here to here. This is a system that mathematically is a nonlinear system. That's simply because in order to describe this in a mathematical, reasonable way, you have to use sine and cosine function, trigonometric functions. And then whatever you're dealing with the trigonometric functions, you know that you're dealing with the non-linearities. And that's the reason that, generally speaking, once you have an equation of motion based on multibody system dynamics, there's no analytical solution available. Not at all. So what you need to do then for the equation of motion is that you have to use a numerical time integration procedure to solve the responses in forward of time. And that's exactly what we do. So let me repeat my story again. So in multibody system dynamics, we make no limitation regarding the magnitude of rotation. So like dealing with this pendulum, the pendulum can rotate it as much as it wants. This means that mathematically we have to describe this motion by using trigonometric functions, nonlinear functions. And because we deal with nonlinear functions, equation of motion eventually will be nonlinear. And because it is nonlinear, there is no general solution, no general analytical solution for that kind of system. So we have to solve the response by using time integration procedure, numerical time integration procedure. So that's how it goes. So then, here comes something that is extremely important to understand, because you must be able to differentiate what's the particle and what's the body. So let's look at the particle. Now the particle, it is something that is assumed to be dimensionless. So it's very small point, very small point. And because it's so small a point, its rotation is immaterial. I mean, its rotation is making no difference whatsoever. So because it's so small, so its rotation is something that you cannot recognize. So that's why particle and a point can be mathematically described by using just its location, meaning translational coordinates. And this is something that is extremely important to understand, because I'm asking over and over again in my in-class quizzes something that is related to rotation of particle. So if there is something which says rotation of particle, that is inherently wrong. So please do not never ever select an option which says something related to rotation of particle, because that's not just possible. Particle do not have these rotational degrees of freedom. Now once you have a lot of particles and you put them together, then that makes you a body. And as we described last week, the body is something that has boundaries, and really the target in dynamics, any dynamics, is to describe every single particle within the boundaries of the body with respect to global coordinate system, which is the one that is located here. Global coordinate system is standing still, so it's not moving at all. Now what we wanted to do here is that we wanted to describe all the particles within the boundaries of the body with help of the body reference coordinate system. It goes this way. So you first describe the translation of body reference coordinate system. That's going to be your vector R. Vector R consists of two components that are Rx and Ry, which are projection in a global X and global Y direction. Then you are counting the rotation of the body reference coordinate system to be more specific. So it's like R plus rotation. And once you account the rotation, you're mapping your description from body reference coordinate system to global coordinate system. Then you just simply accounting all the particles with help of vector U-bar. So this is a kinematics we're using, and this gives you opportunity to describe every single particle within the boundaries of the body. So that's the concept we're using over and over and over again until you look at super bored, but it's very important. Now, what's the concept of this vector U-bar? Vector U-bar is a constant vector, but it's describing all these infinite number of particles. So basically what the U-bar is doing is it's scanning around the boundaries of the particle. So if the body reference coordinate system is located in the box-like body here in the lower left corner, then the vector U-bar will scan from 0 to h, this y direction, and x direction is scans from 0 to w. So it's scanning every single location of the system, and that's how you can account all the particles. How you do that in practice? Well, you're gonna do that in practice by using integrals, but we will get back to that integrals a bit later. Now, similar way, if the body reference coordinate system is located in the middle of this box-like body, then x direction is scanning from minus w divided by 2 to w divided by 2. And the y direction, it scans from minus h divided by 2 to h divided by 2. So it's scanning, so it's accounting every single one, every single particles, and that goes with using the concept of integration. But we will get back to that a bit later once we're looking at the inertia properties of bodies. Okay, one more slide and then comes in class quiz. So prepare yourself. And I know that some of you are very well prepared because I can see that some of you are already logged into Socrative. So this time you can already do so. So go ahead and log yourself to Socrative and you can see the question already. And question is related to role of the rotation matrix. So let me, oh yeah, the Socrative room is LUT, so you can use that. So it's always going to be LUT in this class. So what is this rotation matrix? So this is a kinematics we're using to describe the particle with respect to global coordinate system. And this one here is this rotation matrix. And in a planar case, in two-dimensional case, this is a matrix that consists of 2 rows, 2 columns. So it's 2 by 2 matrix. And this matrix is mathematically orthogonal. So meaning that if you're forming a vector out of this column here, a vector out of this column here, these 2 vectors are perpendicular with respect to each other. And what they actually are, so they are representation of body reference coordinate axis. So they are unit in length and they are perpendicular with respect to each other. So they are this axis here and this axis here, and they are perpendicular with respect to each other, which in a planar case means that they are having 90 degrees angle with respect to each other. So they represent global x and global y axes. So that's their role. And again, what the rotation matrix is doing for you, it is mapping description from body reference coordinate system to global coordinate system. And remember this, particle do not have rotational degrees of freedom. Particle is not having rotational degrees of freedom. So with that, I'm a little excited to see how is that you're performing in this in-class quiz, which says that the role of the rotation matrix, question mark, and you need to select the one that is the most proper definition of rotation matrix. First option is that it describes the rotation of particle P. Read this carefully. Describes rotation of a particle. Okay? Maps body reference coordinate system and the global coordinate system. So he's building the bridge between those 2 coordinate systems. Maps body translation and rotation. Describes the translation of the body A. So those are the 4 choices. And I see that we have today a total of 70 students. I see that there is 84 students following the stream. So are we still having a little bit of hard time to look into Socrative, or is it that some of you are following this using mobile phone and then computer as well? So we get more participants. So momentarily, we're gonna take a look at that. Now, there was a request in chat window that you need to get more time to answer these quizzes. Okay, some of you still have a problem in a Socrative. I'm surprised. I'm surprised because yesterday I uploaded all the information to Socrative. It should be okay. No, and it doesn't really matter when you're answering the question, so you can answer whatever you want. So usually the kind of the, oh, so at least 2 guys are unable to log in. Okay, so for those 2 students, I will give you points. Yeah, this is so use ID without a, 0 in the front. That should help. So can you guys try that? And the Socrates room is this one here. LUT. Okay. All right, guys. I see we have 80 students. So it should be. I can see that we have 82 students that are. Oh, awesome! So now you guys are able to log in. Very happy to see that. And now, please select the correct answer. Please do not select the one that makes no sense. So out of these 4 options, one makes no sense whatsoever. So please do whatever you want, but don't select that one, because that's like hurting me. It's like personal insult to me. So don't do that. Okay, so moving on. So I'm gonna show the results to you. Okay, still a problem. Okay, Okay, so what ID is needed? So it's a student ID number. Student ID number. That's you guys should know your student ID number. Okay, I'm gonna keep the Socrates one. So I will allow you to do this Socrates one. It's gonna be later today that I'm showing the results. Okay, so it still seems to be a little bit of problematic thing. Okay, here's what I'm going to briefly explain to you. I'm not going to spend too much time to this subject matter, because this next thing is description and kinematics in spatial case, 3-dimensional case. And I don't want to spend too much time in this subject matter, because this course is mainly about planar cases. And it's a planar cases because things are a little bit ugly in 3-dimensional space. And they are a little bit ugly because rotations in 3-dimensional space are everything except straightforward. So I want you to be aware of the methods that can be used to describe particles in 3-dimensional space. But I don't want to spend too much time here, because this is stuff that requires a lot of learning, and is a little bit aside from our main objective, which is learning the theory of the simulation. Anyways, so how is a description of particle in the case of 3-dimensional space? Well, as you probably already guessed, so there is no difference regarding the planar and spatial case. The difference comes in the fact that the dimensions are a little different. So in 3-dimensional case, this vector here, which describes the translation of the body reference coordinate system with respect to global coordinate system, have 3 components, which are motion with respect to x, y, and z coordinate axis. And then the rotation matrix here correspondingly will have, well, the dimensions that are 3 columns, 3 rows, so it's a 3 by 3 matrix. Vector u bar, that too will be vector with 3 components. So it's similarly simple, but difficulties comes because of this guy, rotation matrix. Rotations in 3-dimensional space are just nasty stuff. It's just ugly stuff. And it's if you don't believe me, you may go to Amazon.com and type there rotations and quaternions and see how many books are available from that subject matter, and you will be surprised. And it is difficult because we know that the body can rotate in 3 different ways, but mathematical description of that is cumbersome. It is very, very difficult. And there are many different ways, mathematical ways to describe rotations in 3-dimensional space. Today we're going to learn one, and the one is called Euler angles. Euler angles is a concept that is based on 3 successive rotations. So successive rotations is very, very important to understand to kind of get this concept. So let me explain how it goes. So maybe that's the easiest way to understand the concept. So what I have here is that I have 2 coordinate systems that are initially parallel with respect to each other. So I have a coordinate system which is a y and y bar, x and x bar, and so on and so forth. And what I'm doing here is that I'm going to introduce a rotation. And rotation will take a place around z-axis. Here it goes. Amount of rotation is phi. Okay. So that's clear. So that's very, very understandable. But what follows next is this concept of successive rotation. Now we have once rotated coordinate system, which is this bar coordinate system, this one here. What follows next is that I will take a hold of this once rotated coordinate system, and then I will introduce second rotation. And that's where the term successive rotations are coming from. So there is a one rotation after another. So the first rotation and second rotation and third rotations are coupled. So that's the one way to understand this concept of successive rotations. Now, second rotation will take place around once rotated x-axis. Correct, x-axis. And this is a most often used as sequence of rotations when Euler angles are used. So the sequence is z, x, and then the last one, which is 2 times rotated coordinate system, will be rotated again with respect to z coordinate axis. So the most frequently used sequence is z, x, z. Why? Well, I'm not sure why it is so frequently used. I guess because it's coming from the gyrus. So if you look at the gyro, this is not the latest model of the gyro, but anyways, you see that the first axis, this is not the perfect color, but I hope you see my writing here. So the first axis is kind of z coordinate axis. Second one is x axis, and the third one is again z coordinate axis. So I guess it is because of that. But again, the most frequently used is this one here. By the way, that's what I'm going to ask you after a couple slides. So put that in your notes, because I'm going to ask that in a few minutes. And if you're memorizing that, that's going to be very, very simple in class quiz for you. Okay, so this is how it goes. So this is an example. So if you wanted to put the box-like body to certain orientation in a space, you can make it happen with help of 3 successive rotations. So the first one was, oh my God, I'm so bad about these letters. The first one is a phi, then theta, that I know that this is theta, and the second one, final one, is a psi. Okay. You know that you can put the gyro to any orientation in a space. Similar way, you can use these 3 successive rotation, and you can put your body in any rotation in the space. That's how it goes. Now, a little bit about the coordinate systems. So we could use a left-hand coordinate system or right-hand coordinate system. You know, these figures, when you look at these figures, they are based on right-hand coordinate system. Right-hand coordinate systems is, it's my understanding that is more frequently used than the left-hand coordinate system. And how you can get these axes? Well, use your right hand. So that's how it goes. So I took a picture of my hand. So I have here a thumb that is a little bit bended. X, Y, and Z. And then the positive direction you can get when you're using your other hand. And you put, if this is your, here's my camera, so if this is your left hand coordinate system, you use your other hand and put your thumb towards the coordinate axis. Your rest of the fingers are telling what's the direction of positive rotation. So this one is a positive rotation. By the way, you see some of the pictures that I'm using in the YouTube, I'm using like this, or this is like another coordinate axis, left hand side or right hand side. So please use that when you see me in the university corridor. So don't say like hello Aki, but say Multibody. That will make me so happy, because this is a kind of the thing we're doing in three-dimensional space. Most of the stuff we're discussing here is still going to be planar cases, so you really don't need to use your fingers like this. But anyway, so this is our way to say hello. Hello. Okay, so with that, so let's move on. Okay, so what is what we can do with these rotations then? Because we need this 3x3 matrix. We are after that. Okay, so each one of these rotations we can describe by using 3x3 rotation matrix. And this may look a little bit scary in the beginning, but actually it's not bad at all, because this is something that you're very much familiar with. Because the first rotation can be described by using this 3x3 matrix. Okay, what is that we have here? First of all, we have one column that is not changed, so it's still unit in a length, and it's this one here. This is obviously describing where the rotation takes place. So it's z coordinate axis, because z coordinate axis is 0, 0, 1. This 2x2 submatrix is exactly same that we are used to deal with in planar cases. So not too difficult. Second one. Rotation axis is here, X. And my 2x2 rotation matrix is here. So it's okay. My final one, rotation axis, Z, and 2x2 rotation matrix, it's here. So again, let me repeat, because that's what I'm going to ask you. Sequence of rotation is Z, X, Z. Okay. Now, how you can get this final 3x3 rotation matrix? Well, that one you can get by multiplying these successive rotations, the rotations together. And then you can get the final description of rotations, and that's shown here. Please do not try to memorize it, because, that's not at all needed. But memorize the concept, they understand the concept we're using here. And then, my second in-class quiz, but prior to that, let's take a look how is our success rate from the first in-class quiz. Hold on, I'm here. I want to show it to you, because I think this is I'm kind of sensing that this is a good stuff. Oh, not that big. I want to make it a bit smaller. Okay, success rate. Ready to see the results. Okay, success rate is good. Success rate is good, but we have good news and we have a little bit of bad news. Okay, so good news is, let's get started from the good news. Good news is this. Almost 80% of you were able to answer correctly to this in-class quiz. So you know that the rotation matrix is here to map body reference coordinate system and the global coordinate system. Then the bad news. Bad news is this. Particles do not have a rotation. So if I'm asking something related to that, please always ignore that possibility, because that's just simply not correct option. Okay, so 11% of the percentage of you, please memorize this. Particle do not have rotational degrees of freedom. Okay, so let's put this aside here. And here's my second in class quiz. So let me put that on. So it's on now, so you can answer now. In every angles, an often used sequence of rotation. One we just look at is, well, here are the choices: X, Y, Z, ZYX, ZYZ, ZXZ. And then a little bit of additional stories related to this stuff next week. But other than that, I think we're going to leave a description of rotations in three-dimensional space. And you know that I organized this week a lecture a little bit different way than last week, because I put that team session to be middle of the lecture. So I think what I'm going to do here is that I will hold this streaming and I'm going to move on to Teams. You are able to meet me in a Teams. And if you have any comments, any questions, any complaints, jokes, anything you want to share with me, please join the Teams and we can discuss about whatever you want. And whatever you've done, then we're going to move back to the stream. Okay? So with that, please open the Teams and communicate with me.